Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the step response of an RC circuit, which is located to the left here. And essentially what we want to do is analyze the circuit for two cases, where case one is when t is less than 0, or when the gate here or this switch here is open, and case number two is when t is greater than 0, or in this case here, when the gate or the switch is closed. Okay, so let's go ahead and define what a step response is. So the definition of a step response is the step response of a circuit is its behavior when excitation is the step function, which may be a voltage or a current source. And again, remember the step function, which is denoted by u of t, is essentially 0 from t is equals to negative infinity to t is equals to 0. And then it shoots up to 1 for t is equals to 0 to t goes to infinity. So any circuit which, when a voltage or current source is applied to, has an excitation that looks like this u of t, is called the step response of that circuit. So I hope that makes sense. So let's go ahead now and dive into the two cases that we want to evaluate. So for the first part, we want to look at case number 1. And essentially we want to look at when t is less than or equals to 0. And again, this is when t is equals to 0 minus, or t is equals to 0 plus. And the reason why, again, these are the same is because voltage of a capacitor cannot change instantaneously. And I've talked about why this is the case in a past video I made, which I will post in the top right hand side corner of this video. And essentially what we want to first note is some notation simplifications. And this notations will follow for the remainder of the video, where I'm going to say that Vs of t is equated to just Vs. V of t is the same as saying Vc of t, or the voltage across the capacitor, which I'm going to refer to as V. And I of t, which is the current through the capacitor, which can also be notated as Ic of t, I'm simply going to call I. So now, based on our previous learnings, we know that V, or the voltage to the capacitor, let me say V of t, when t is equated to 0, is basically V of 0 minus, which is going to also just be this V of 0. So it's just going to be the initial voltage at my capacitor when the switch is open. It could be 0, or dependent if the capacitor was previously charged by some other source other than this Vs of t. It could have this V naught. It could be a value or another constant other than 0. Long story short, this VO is essentially the initial voltage across the capacitor. And again, since voltage across a capacitor cannot change instantaneously, we say then that VO minus is equated to VO plus, which is also just VO for simplicity. And this is our conclusion for case 1. Now for the next case, call this case 2, we want to essentially consider the case where t, or the time when the switch has been closed, and now Vs of t is able to charge my capacitor. So then what we're going to do is consider that this is when t is equals to 0 plus, or t is greater than 0. And we're going to write a KVL equation. And I've done a video on this in the past, and I'll post that in the top right hand side corner of this video. So essentially what we can say is that minus Vs plus IR plus V must equate to 0. So then minus Vs plus C times dV over dt. And again, this here is essentially the current through a capacitor, I, times R plus V must equate to 0. Let me go ahead and multiply this entire thing by 1 over RC. So then what we get here is that we get dV over dt plus V over RC is equals to Vs over RC. And again, just for clarification, V is equated to V of t and Vs is equals to Vs of t. Just, I don't want to keep writing Vs of t and V of t. So this makes it more clear and more easy to follow. And this is what we call our first order linear original differential equation, or ODE, which we have to solve for. Okay, now let's go ahead and solve for the ODE. And essentially, we want to rearrange our terms. I'm going to say then that dV over dt is equals to minus V minus Vs over RC. So what I'm going to do is I'm going to multiply V minus Vs on both sides, and then multiply by dt on both sides. So it's going to look something like this. I'm going to multiply everything by dt over V minus Vs. So then what I get is dV over V minus Vs is equated to minus dt over RC. So let me go ahead and integrate this from VO to V. So essentially from the original voltage across the capacitor to a given voltage when the switch is closed. And then integrate this from 0 to t. So time is equals to 0 to time is equals to a time t. And what we should note here is that V is the independent variable, or the variable that I'm taking the integral of, and Vs is a constant. And here RC is basically just a constant. So let's continue. And we could say then that this becomes ln V minus Vs. And we're going to integrate from VO to V, has to equate to minus T over RC from 0 to T. So then this becomes ln V minus Vs, right? I'm plugging in V into this here. And then minus ln VO minus Vs is equated to minus T over RC plus 0. So then what we can do is say then that this here, we're subtracting ln's or logs from each other so we can divide them, right? So then what we can do now, I'll do a box here, and I'll say then that this becomes ln V minus Vs over VO minus Vs must be equated to minus T over RC. And again, to get rid of an ln, we take the exponential of it on both sides. So then what we get is V minus Vs over VO minus Vs is equated to e to the minus T over RC, which we call this e to the minus T over tau, where tau is equals to RC. And then we basically want to solve for this V here. So that's our end goal. So essentially what I'm going to say is then that V minus Vs is equals to VO minus Vs e to the minus T over tau. So then we can say then that V is equals to Vs plus VO minus Vs e to the minus T over tau for T is greater than 0. And this is my solution for case number 2. Okay, so let's go ahead and write everything more clearly so we can draw some conclusions about both these cases. Okay, so the first thing we can say is that this V of t is equated to this VO, or again, my initial value, when t is less than 0, less than or equals to 0. And then we can say then that V of t is equals to Vs of t plus VO minus Vs of t e to the minus t over tau, where tau is equals to RC, or my time constant is equals to RC. And this is for t is greater than 0. And this is what we refer to as our complete response, or our total response in some books, of the RC circuit to a sudden application of a DC voltage source. So the second thing we want to conclude is what's called the more general complete response. I'm going to say then that V of t is equated to this V of 0 at t is less than or equal to 0. And then I'm going to say then that V of s of t, it saturates to Vs of t. So V of infinity is what I'm going to call it, plus VO is just going to be, again, the initial condition minus V of infinity times e to the minus t over tau, for t is greater than or equals to 0. And again, this is what's referred to as the general complete response. And you might see other textbooks refer to this as the FIFE equation, FIFE. And this stands for final, initial condition, final, and an exponential at the end. All right, so this is where this term 5 comes from. And it's a very, very important equation to know and to memorize. And you can really solve any RC circuit using this concept. So let's keep on going here and consider a third thing. And what we want to say is that we want to assume VO, which again is just V of 0. Let's consider it to be 0. Okay, so my capacitor is uncharged initially. We're going to see then that V of t is going to be this 0, because V of 0 is 0 for t less than or equals to 0. And again, for t greater than 0, we're going to see that it's going to pan out or simplify to V of infinity times 1 minus e to the minus t over tau, where again tau is equals to RC and t is greater than 0. So then this is what we refer to as the complete voltage step response of the RC circuit. And essentially, this is when the capacitor is initially uncharged. And again, the reason why I refer to it as the step response is because it has the behavior of the unit step response, which, again, the graph looks like this. It's 0 for any time lower than t equals to 0. And then as we go to t goes to infinity, it has this type of curve. And again, it saturates at this V of infinity. All right. So it just keeps going like that. And this has a similar behavior to the unit step response. Okay, so the last thing we want to do now is conclude some information about our current I of t in the circuit. So that the next point, call it point 4, since I of t is equals to C dV over dt, this becomes c d over dt, and we have v of 0, v of infinity plus v of 0 minus v of infinity times e to the minus t over tau. This is for t less than or equal to 0 and t greater than 0. So then I of t becomes the derivative of a constant is simply 0 for t less than 0. And then the derivative of this function here is going to be 0 plus minus c over tau times v0 minus v infinity e to the minus t over tau for t greater than 0. This is less than or equals to. So what we can do is we can notice that if we distribute the negative symbol, this becomes minus and this becomes plus. So, and we notice that tau is essentially RC. So then the C's cancel out. A cleaner version of this becomes V of infinity minus V of 0 times e to the minus t over tau over r. And again, this is for t greater than 0. And this here is referred to as the general complete current response of an RC circuit, where the last thing we want to note is the step response, or when VO for VO is equals to 0, I of t is basically going to be, again, the 0 for t less than or equal to 0. And then this becomes V infinity over R times e to the minus t over tau for t greater than 0. And again, this is the complete current step response of an RC circuit. And again, the graph, if you want to graph this, basically from t is less than 0 to 0, we get basically my I of t. There's no current flowing through it, right? It's an open. And then it shoots up, right? Because when e to the 0, this becomes 1. So it shoots up to v of infinity over r. And then it slowly decays back down to 0. All right. And this here is a behavior of a step response. Okay, in the next video, I'll be doing 2 examples along the topic of step response of an RC circuit. If you like this video, please give it a thumbs up and please share the video to your classmates and colleagues. And if you like what the YouTube channel is providing, please consider subscribing to the channel. It really helps the algorithm. Thank you.